All right, so this is the point in the semester, we're nearly to the end of the semester, but this is the point where we kind of switch gears a little bit. All right, so all semester long, we've been focusing on this idea of the derivative and what does the derivative mean? What does the derivative tell us? We kind of reached the pinnacle of derivatives as far as this class is concerned last week, and when we were talking about the first derivative test and the second derivative test and all these things that we can learn about functions using derivatives. Now we're switching gears, and what we're going to see in the next couple of lessons is going to seem pretty disconnected from anything we've been talking about so far, but you'll start to see the connection soon enough. All right, so in this lesson you're going to be learning about how we can calculate area under curves, and I'll be more specific about what I mean by that in a second, but let's start with an example. So suppose you travel at a constant velocity of 5 meters per second for 3 seconds. How far did you travel? If you think about this for a second, it's not that hard to figure out. 5 meters per second for 3 seconds means you went 15 meters, right? It's your velocity times time gives you your total distance. All right, now this question that you can answer pretty intuitively, we know that the answer here without much effort is 15 meters. Let me show you what this looks like graphically. So graphically, we'll say that this horizontal axis is the axis for time, which in most applications, that's what it is representing. And let's graph our velocity function. If our velocity function is constantly 5, we have this function v of t, our velocity function is just always 5. All right, so a constant function is pretty straightforward. You just stay flat forever. It's always 5. Now, how does this question about the distance we traveled relate to the graph that I just drew? Well, let's say we start at time 0, we go for 3 seconds. 1, 2, 3. 3 seconds. Now, this 15 that we got, how it relates to this graph is, let me just draw a little rectangle here. I'm going to look at what's happening below my velocity function between time 0 and time 3. What is the area of this rectangle? Well, obviously area is base times height, length times width, however you want to say it. The area is, I've got a base of 3 and a height of 5, it's 15. So if I give you a velocity function and I tell you to find the total distance that you've traveled, really I'm asking you to find the area underneath this curve. What is the area over this time interval under my velocity function? All right, so we can kind of generalize this. If I have some function v of t, if I look at the area under the curve over some time interval, that area is going to equal my total distance traveled during that time. All right, so what we're going to be looking at in this section is how do we find the area under a graph? And now specifically when we talk about area under curves, the idea of the area under a curve, in this case our curve was a straight line, but you can come up with other functions that aren't a straight line, and what if you want to know the area under those? How do we find that area? Now specifically when we say area under a curve, we mean the area between that function's graph and the x-axis. Area between graph and the x-axis. At least in, as far as we're concerned in this section, that's what it's going to mean. We could also look at the area between the graph and the y-axis, but we're not going to worry about that here. As far as we're concerned, when we talk about finding the area under some curve, we're talking about the area that lies between the graph of that function and the x-axis. All right, so now what we need to think about is, in this case, it was pretty simple. My velocity function was constant. What we want to think about next is we don't always travel at a constant velocity. We slow down, we speed up, our velocity changes. How can we find the area under the velocity graph? In other words, how can we find the total distance we travel if our velocity is not constant? Let's look at that on the next slide. So here let's do a similar question. We want to find the total distance traveled during the first 3 seconds, just like we did on the previous slide. But now our velocity is not constant. As we travel, we're slowing down and then speeding up and then slowing down again. Our velocity is changing as time goes by, which is probably a little bit more realistic. Now, if I want to find the total distance traveled over some time interval, the first 3 seconds, that's exactly what we talked about on the last slide, total distance traveled. If I'm given a velocity function, notice this is not the distance function, this is the velocity function. My total distance traveled is equal to the area under my velocity function. So the area under the graph of v of t. And the time interval that we're talking about here over the first 3 seconds would be the interval from 0 to 3. All right, so let's think about this for a second. I've got this function v of t that's not constant, and I'm looking at the interval from 0 to 3. How in the world can I find the area under this graph? On the last slide, finding the area was pretty easy because it was a rectangle. This is definitely not a rectangle, and in fact it's not any of our typical geometric shapes. If it were a triangle, fine, we know how to find the area of a triangle. If it were a trapezoid, I don't know, maybe we could look up the area for trapezoids. But here, this isn't any typical geometric shape, and this velocity function, it's not even made up of straight lines, it's a curvy line, so we can't use any typical geometry formulas to get this area. So what can we do? What we're going to do is we're going to start by finding a way to estimate the area. Alright, so see if you can think up of a way based on what we've already talked about with the area on the last slide. See if you can come up with some way to estimate this area. And we'll look at that on the next slide. All right, so we don't know a way to find the exact area under this graph between 0 and 3, but let's come up with an estimate. In fact, I'm going to be more specific. We're going to estimate the total distance traveled, and I want this estimate to be an underestimate. Alright, so let's see if you were able to come up with a way to estimate this area the same way that I'm going to here. There's actually lots of ways we could estimate it. I mean, one thing we could do is we could just take some speed that we were going, some velocity that we had, and let's just pretend like we're going that same speed the whole time. Well, then we have a constant velocity, and good, there's an underestimate, right? The area under this constant function is an underestimate. And this relates back to our first slide because now we're just finding the area of a rectangle. All right, so that's pretty straightforward. That wouldn't be a very good estimate though, but it would be an underestimate. What if I asked you to make that estimate better? Well, we can refine our rectangle, right? I can break this into smaller chunks. Let's look at some subintervals. Let's look at the interval from 0 to 1. Let's look at the interval from 1 to 2 and the interval from 2 to 3. Okay, over this interval from 0 to 1, if I want to estimate the total distance traveled during that first second, again, and I want it to be an underestimate, let's just pick this low point and assume that we traveled that same velocity over that entire time interval. Okay, so the area of this rectangle would be your total distance traveled during the first second. And then you can kind of guess what we're going to do the rest of the way. Over this next time interval from 1 to 2, if we want this to be an underestimate, let's pick the lowest velocity over that interval. So that would be about here because the rest of the way I'm speeding up. And let's pretend like I'm going constantly at that speed over that interval. And now let's find the area of this rectangle. If I find the area of this rectangle, then I'm finding an estimate to the total distance I traveled during that second. All right, and then for my third second, from time 2 to time 3, same thing. Find the lowest point on that interval and pretend like you were going that exact speed during that entire time interval. All right, so maybe it's around here. Let's pretend like we weren't actually going this speed the whole time, but just to make the computation easy, let's pretend like we were going this speed the entire time. Our velocity was constant over that interval. Well, then again, if I find the area of this third rectangle, then I'm getting an estimate to my total distance traveled for that third second. So then if I want an underestimate for the total distance traveled for the first 3 seconds, I just add up these 3 areas. I'll call this area 1, area 2, and area 3. My estimate would be the sum of those 3 areas. And now you can kind of maybe guess where we could go from here. What if I said, okay, that's a good underestimate. Make that estimate better. How can you make it better? Well, we make it better by doing more rectangles, right? Every time I do more rectangles, I'm getting a more accurate estimate. And I'm getting closer and closer to the actual area under the curve, right? Right now, the area under the curve, okay, this is a decent estimate to the area under the curve, but there's a whole lot of space that I'm missing, right? I'm not getting everything. So this is an underestimate. But as I refine this picture and do more and more rectangles, my estimate is getting better and better. So if I break this up into let's say half-second intervals, then I would be looking at more rectangles. And I could still give you an underestimate, but my underestimate would be better than it was before. So now if I add up the area of all these blue rectangles, I'm still underestimating the area. I'm still not getting the exact distance traveled, but aren't I closer to getting the total area under the curve now? The total area that I'm missing is a lot closer to the actual answer. I'm just missing a little bit now. There's still some spaces that I'm not quite getting with these 6 rectangles, but I'm at least closer than I was when I did 3 rectangles. So if I want to make my estimate better, then I can do more rectangles. And this is going to be one of the ideas that we talk about. And we started the very beginning of the semester talking about limits. Well, can you imagine where this is headed? Maybe we want to do the limit as the number of rectangles goes to infinity, because as the number of rectangles increases, we're getting closer and closer to the real answer. Okay, so this is kind of where we're headed with this. Now let's try something a little different. What if I ask you to estimate the total distance traveled over the first 3 seconds, but now instead of an underestimate, I want you to give me an overestimate. What can you kind of guess based on what we've done, what's going to come next? For the underestimate, we did subintervals, and on each subinterval we picked the low point. What should we pick for the overestimate? We should pick the high point. So again, let's just do 3 subintervals. Like we saw on the previous slide, if we did more subintervals, we would get a better estimate, but let's just do 3 this time. Over this first subinterval from 0 to 1, let's pick the highest point. It looks like it's over here on the right end. And fortunately, you guys know how to find a max and a min over a closed interval, right? We learned how to do that a few sections ago in chapter 4, really back at the beginning of chapter 4. So if this were some function without a graph, well, we could find the high point over some interval using what we know about derivatives. But anyway, let's just draw the picture here for what our overestimate would look like. So if I want to pick the high point and then assume that I'm traveling that speed constantly over that interval, then the area under this rectangle would give me an estimate to how far I traveled during that first second. From time 1 to time 2, pick the high point on the interval, draw the rectangle, find the area of that rectangle, base times height. The area of that rectangle is an estimate to your total distance traveled from time 1 to time 2. From time 2 to time 3, pick the highest point. I don't know, maybe it's around here. And then draw your rectangle, and the area of that rectangle gives you an estimate to how far you traveled from time 2 to time 3. So now if I want to overestimate, I pick the highest point on each subinterval, and picking the highest point on each subinterval, draw my rectangle, and now add up the areas of these rectangles, and I get an overestimate. Okay, and again, we can make this estimate better if we do more rectangles. But notice here, this total area, we've got some extra space here that we're counting up. That really isn't underneath my graph. All right, so we're getting a larger area than we want, but it's at least a decent estimate. We make the estimate better with more rectangles. All right, so we found the underestimate using the low point of each subinterval. We found an overestimate using the high point of each subinterval. Let me show you one more thing that you'll be doing in your homework for this section. You'll find an estimate using the midpoint of each interval. So we're going to estimate using the midpoint of each interval. So this first interval from 0 to 1, the midpoint would be at 1/2. I go from 1/2 and find where it hits the graph, and then draw my rectangle over that entire interval. All right, so my time interval from 0 to 1, here's my rectangle for that interval. From 1 to 2, find the midpoint, so that'd be 1.5. See where that hits the graph, and use that as the height of your rectangle over this second interval from 1 to 2. So then draw your rectangle over this interval, and there's your rectangle for the second interval. For the third interval from 2 to 3, the midpoint would be at 2.5. use that to find the height of your rectangle, and then draw your rectangle over that interval. Now, this idea of using the midpoint is you can usually get a better estimate with 3 rectangles here than we did when we did the underestimate or the overestimate. Notice here, sometimes the rectangles are below the graph, sometimes it's overhanging, there's some extra area. So maybe things kind of balance out and get us closer to the actual area or the actual distance that we've traveled. All right, so this midpoint, the idea is that maybe sometimes it'll be slightly under the actual answer, maybe sometimes it'll be slightly above the actual answer, but it should be roughly close to the exact answer. And again, we can still make it even better by doing more rectangles. So we've talked about all different kinds of ways that we can come up with an estimate to the area under our curve, which tells us if this is a velocity function, that tells us the total distance we've traveled. And this isn't the only application that we'll run into. This isn't the only reason we want to find the area under a curve, is to take velocity and find the distance traveled. This is just to kind of give you some motivation behind what you'll be doing in your homework. In your homework, basically all you're doing is adding up areas of rectangles. You have to find the base, find the height, and add up those areas of rectangles. That's all you're doing in your homework. But I want to show this to you in the context of, finding total distance given velocity, just so you know kind of at least one application of where this all comes from and why we might want to do this. You'll learn other applications further down the road. One last thing I want to show you though is we looked at all different ways to do this estimate, but there's something else that we could change. If you think back to the very first slide, I said that we could do this over any time interval. Every single one of these examples, we've done it over the interval from 0 to 3. But really, if I want to know my total distance traveled from time 2 to time 3, I could do that. What if we change this and say, let's find the total distance traveled, or estimate the total distance traveled, instead of doing it over the first 3 seconds, let's do it during time 2 to time 3. So the interval from 2 to 3. So now what we're really focusing on is this interval here. We don't care about the area under the rest of it. We just want to know what is the actual area under this curve over this interval. All right, now again, this is not a straight line up here. It's a curve. We don't have a nice geometric formula, but we should know by now how we're going to come up with our estimate, right? Our estimate is going to come from rectangles. And usually on this type of question on your homework, they'll tell you how many rectangles to use. So they may say the interval from time 2 to time 3, and they'll say to use 5 rectangles. So if I'm going to go from 2 to 3 and use 5 rectangles, then I have to break up my interval into 5 subsections, right? So these 5 subsections will give me the base of each of my rectangles. So this first one would be 2 1/5, 2 2/5, 2 3/5, 2 4/5, and then 2 5/5. So you've got 5 rectangles, and they'll also specify how they want you to do the estimate. If they want you to use the midpoint, then you find the midpoint of each of these intervals. If they want an underestimate, then you'll do that, but basically just follow whatever directions they give you, whether they want an underestimate or overestimate, however many rectangles they want. Add up the areas of the rectangles, and that's your answer. Okay? Now, the other thing I'll mention is all along the way, I never told you what our velocity function was. In the next couple of videos, you're going to be given a specific function where you could answer this really even without seeing the graph. because how are we getting the height of these rectangles? So for example, if I drew this rectangle, let's go back to this. Is kind of messy over here. Let's go back to what we did a second ago with the midpoint. And I went to the x value 1/2. And I used that to get the height of my rectangle. Well, what's the height of the rectangle? I can know the exact height of the rectangle by plugging my x value into my function. So my height is whatever I get when I plug 1/2 into my function, right? Because this right here is v of 1/2. All right, so the heights of the rectangles will come from whatever your velocity function is, or whatever your function is. It won't always be given in terms of velocity. All right, so the height comes from plugging your x value into the function, and then the width just is based on how wide your subinterval is. In this case, our base would be 1 because that's how wide that interval is. All right, so if we're doing base times height, the base is the width of the interval. The height is what we get when we find our y value, when we plug some specific x value into our function to find our y value. All right, so I did all of this without telling you any specific function v of t. The next video or two will show you more specifically how that'll look if you were told a function to use.